Bismillahirrahmanirrahim. My name is Zahur Khan, lecturer in physics, Government Degree College, KD Township, Kohat. The course title is Waves and Oscillation. Course code is PHY103. Today topic is general wave equation, and I wish the pandemic be ended soon, so that we may resume the physical classroom environment. Well, the propagation of waves is actually the transportation of energy without net motion of the medium's particles, like water waves, waves on string, sound waves, and light waves. This is the picture which depict the water waves. If we drop a stone in a pond, then there will be some sort of disturbance produced on the surface of the water. This disturbance will be propagated throughout the water surface. Here the particles will vibrate up and down about their main position. However, the net motion of the particles is zero, because in one cycle the net displacement covered by the particles in vibration is zero. So that's why we can say that the net motions of the medium particle is zero. Here we have the waves on string, where the string particles vibrate about mean position in vertical directions. Here too the net displacement of the particles during one cycle is zero, although in spite of the net zero motion, the waves propagate from one point to another point. This is the picture which depict the electromagnetic waves. In electromagnetic waves, electric and magnetic fields actually propagate about their mean positions. So for any waves, there must be a waving parameter that will be changed with respect to time and position. For example, in case of water waves, displacement will be changed with respect to time and position. Here in case of string, the displacement is changing with respect to time and position. The difference between the two is that here we have a waves in 2 dimension, while here we have a waves in 1 dimension. While in case of light waves, the waving parameter, I mean the function which is changing with respect to time and position, is electric or magnetic fields. While in case of sound waves, the waving parameter is pressure. So it is the pressure that will be changed with respect to time and position, because in sound waves we have compression and rarefactions. And compressions, the pressure is higher as compared to the rare. Well, for the derivation of wave equation, we suppose that there is a string vibrating along y-axis. The pulse of wave is propagating along x direction, and further we suppose that the tension in the string be T, while the linear density of the string be mu, and we suppose in ideal case where there is no damping involved. So this is the picture that show our case. Here we have a pulse which is propagating from left to right along the string, and remember this is the y-axis along which the string's particle vibrate, while this is the x-axis along which the waves is propagating. Well, this picture showing a section of string of length dx, because of a slight curvature in this length element, there is a net force acting along y-axis. The tension acting the tension at the upper end of the string is making angle theta 2 with the x-axis, while at the lower end of the string the angle subtended by tension T with the x-axis is theta 1. So from this particular figure we can say that f of y is equal to t sine of theta 2 minus t sine of theta 1, which is giving us a net force acting on the string. Here f of y is equal to t sine of theta 2 minus t minus sine of theta 1. We have taken the t common. Now if the displacement is very small, I mean the displacement of the oscillator from the mean position is very small, then sin theta 2 will be equal to theta 2, while sin theta 1 will be equal to theta 1. Remember, this is possible only if we measure the angle in radian. So using these values and equation 2, we will get f of y is equal to t curly theta, where curly theta is the difference in angle which is shown here, theta 2 minus theta 1, giving us curly theta. Well, this is an exaggerated figure of the string section of length dl. Here f of y is the net force acting on the string along y-axis, while here this is the angle, remember, which is the difference between theta 1 and theta 2. So from this figure we can say that tangent curly theta is equal to curly theta. This is the case when the measure of angle is very small and the unit of measurement is radian. From the fundamental geometry, tan curly theta is equal to curly y by curly x, perpendicular by base. In that case, this is the perpendicular while this is the base. So using this value in equation third, we have f of y is equal to t curly y by curly x. Let's say this is equation number 4. Now from Newton's second law, F is equal to ma, we can modify this equation, rather instead of modification of equation 4, we can write a new equation, because this net force is given by the Newton second law. Here F is equal to f of y, while m is the mass of the moving object, which is dm here, the mass of the string element. A is the acceleration of the moving object. Here the acceleration, since the acceleration is the double derivative of displacement, so a is replaced by curly square y by curly t square. Using the definition of the linear mass density, mass per unit length, we replaced dm by mu curly x. So equation 5 becomes f of y is equal to mu curly x into curly square y by curly t square. Well, comparing equation 4 and 6, we have curly square y by curly t square equal to t by mu into curly square y by curly x square. So from the velocity of the wave in the string, we know that v is equal to t by mu, where mu is the linear mass density. Taking square, we will get t by mu is equal to v square. So replacing t by mu by v square, we will get 1 over v square into curly square y by curly t square equal to curly square y by curly x square. This is the one-dimensional case where the wave is propagating along one dimension, like the waves pulse propagating along the string. In case of two dimensions like water waves, this equation will become 1 over v square curly square r by curly t square, which is equal to curly square r by curly x square plus curly square r by curly z square. Here r is the waving parameter, which is changing with respect to time and position, and it is given by r is equal to x square plus y square under the root. This is, remember, an example of like water waves. In case of three dimensions like sound waves or electromagnetic waves, here we suppose that we have sound waves. So this equation will now become 1 over v square into curly square p by curly t square equal to curly square p by curly x square plus curly square p by curly y square plus curly square p by curly z square. Here p is the pressure, which is the waving parameter in case of sound waves. So that's end of today's lecture. I hope that you will find it fruitful for your understanding.